Now we're starting our final chapter, chapter 36, which talks about the special theory of relativity. And so let's talk about this. So we'll start out just with the kind of description of what's going on. So it turns out Newton was wrong about certain things. Well, he was sort of wrong. So he was wrong in different kinds of regimes that were really the kind of things that he didn't have much experience with. So first of all, he was wrong for really fast objects. So everything we're talking about today, pretty much you need to get really close to the speed of light for it to generally make a big difference. This is what we call the special theory of relativity. He was also wrong for really small objects, so the size of an electron. And this is the realm of physics called quantum mechanics. It really was the birth of chemistry. He was wrong for accelerated motion or very large gravitational fields, and this is Einstein's general theory of relativity. And so these are cases that don't come up very often for him, and so you can kind of understand that he was off by that. And so it's important to keep in mind that Newton's laws, while technically incorrect, work really well in most cases. Okay, it's just these really extreme situations where it's off a little bit. However, all these theories have remarkable conclusions, and so we'll challenge a lot of our ideas. And collectively, these theories are known as modern physics. It's kind of funny because the actual time period that they happened were anywhere from 1905 to 1930, but this is what we consider the modern physics. So we'll start out, and so I think, at least for me, a lot of the early stuff in a relativity chapter seems kind of like, why are we going through this? It seems like we're being really technical, but you kind of have to talk about this stuff. And so we're going to start with Galileo and Newtonian relativity, and we'll make some definitions. So the first definition is what a reference frame. A reference frame is your place of reference that you make measurements from. And so this can be anything. It can be a person moving along in a car or something like this, but just wherever you're making the measurements from. And we have a very special one. It's called an inertial reference frame. And this is just a really fancy way of saying that the reference frame that you're measuring from cannot be accelerating. It can move at a constant speed, but it cannot be accelerating. That's all that means. It's kind of a fancy way to say that, but that's all that means. And the relativity principle in Galileo's version is the laws of mechanics are the same for all inertial reference frames. So let's just start real quick, give it a try. Which one of these cases is a good approximation of an inertial reference frame? All right, so you got B, hopefully. So a plane flying at a straight and level at constant speed has no acceleration. Okay, a jet plane during takeoff is going to be speeding up, so its velocity, its speed will be changing, so it has acceleration. And a jet plane turning at a constant speed, because it's turning, its direction is changing, and so it's not, it'll be accelerating as well. So B is the only case that's not accelerating. And again, that's what an inertial reference frame means. It cannot be accelerating. And so here's a picture of some reference frames. So you'll get a lot of these kind of pictures around when you're talking about relativity. And so there's usually two frames. The S frame is the one that's not moving. So maybe we're in this frame making calculations. And the S prime frame is generally the one that's moving. And so they said up here that these two frames were sort of coincided at time equals to 0. But this frame is moving with some velocity, so it moves off with some velocity. And here's just another kind of picture to sort of talking about this. And so in this case, there's an event. So an event is something that happens, and an event has 4 coordinates. It has time, and it has x, y, and z, z coordinates. That's how they measure an event. And so usually we have 3 coordinates. Now we have the 4 coordinates. And you can see in this picture here, sorry about this, that this particular event, this firecracker, okay, has a different distance. And so here it's x measured from the unprimed frame, and it's x prime measured from the primed frame. So basically what they do is they just, for the primed frame, you just take all the same coordinates and give it a prime. And typically we just don't show the z coordinate because it's kind of tricky. It gets busy showing these 3-dimensional pictures. Now here's the equations that you can transfer back and forth between the primed frame and the unprimed frame. All right, and basically, this thing is moving in the x direction. So in this case, it only really, in Galileo's, it only affects the x direction. All right, and basically, as time goes on, the x prime will be different than the x, and it'll be different exactly by velocity times time. And that's what you see in this picture here. You can then take these equations and do the derivatives of them. All right, and so for instance, if you got x equals x prime plus vt, if I take the derivative of all the sides, I get dx dt equals x prime, so it's dx prime dt, and then here it would just be plus v, since the derivative of this, remember, the v always has to be constant. So that's really important. It always has to be constant. And so this just turns out to be the velocity in the x direction equals the velocity in the x direction primed plus the velocity. And one thing that they do here is that they'll start using u as a velocity. And the reason is because you have this velocity that sort of offsets your two frames, and so you want to be real clear. That's the sort of the relative velocity between the two frames. These are the velocities of your objects in those two frames. And finally, we have a picture here that shows a force. And so this is what it means. And I know for me, it was really hard to get this when I first learned this stuff, what they really mean by it. Okay, but this idea of relativity means that the laws of physics are the same in all the frames. And so here you can imagine that we do F equals ma. Okay, and so there's some force and there's some mass that's going to feel some acceleration. Well, if you look at these equations, all right, so here's my equation. Something kind of like this here. If I take the derivative of both sides of this setup, okay, I get something kind of like this here. And this guy goes away because it's a constant velocity, so that goes away. So I basically get that the acceleration in the x direction equals the acceleration in the x direction prime. So having a relative velocity does not affect your acceleration. So if you guys, if there was some people here moving with this frame, or if there's some person that was standing still, okay, they would see some force acting on this object, and they would see it having some acceleration. They could both use F equals ma, and they'd get the right answer. And so that's what it means that the F equals ma works in both frames. And it's because of this here, because you know these two accelerations have to be the same. This common velocity does not affect the acceleration. It would, however, if one of the frames are moving with an acceleration. So that's why this only works for inertial reference frames. So let's just sort of see how this works. So here we have two frames, S and S prime, and we've got a bunch of speeds. We're going to talk here about particle 1. Particle 1 in the unprimed frame, in the frame 1, is going with a positive velocity of 2 meters per second. This frame, S prime, is moving with a velocity of -4 meters per second. So what is the velocity of ball 1 relative to Y prime? All right, so hopefully you got that it's 6 meters per second. And so here I'm going to use my equation that looks like this. I'm solving for the u primed velocity. So you can do this a couple different ways. So here's the technical equation way. My equation looks like this here. And so what is my velocity? Well, the unprimed frame, my velocity is 2 meters per second, and that's a minus the relative velocity of the frame you're going into, which is -4 meters per second. So when I add that up, it's 6 meters per second. Now you can also kind of do this in your head. If you think about it, right? So this particle is moving forward with 2 meters per second, and the frame's moving backwards. So these two speeds, okay, increase the speed of 1. So because this guy is moving towards particle 1, it's going to seem like particle 1 is coming at it faster. And that's what this comes up with here. All right, so now things were going good, and then E and M happened, which we were just finished talking about. And if you remember, we predicted, or not we, but Maxwell predicted waves that would travel with this speed here. Okay, this is light, so these are electromagnetic radiation. The problem is he didn't have any mechanism to alter this speed. His equations just said it's always this speed no matter what. And so people were confused. They didn't know what to do. And so Einstein came around was the first person that really was able to answer this. And so he has his postulates of special relativity. And so here's the postulate as I usually give it. Here's the one as Knight gives it. It's basically the same thing. It just says the laws of physics have the same form in all inertial reference frames. So they say that the laws of physics are the same in all inertial reference frames. It's the same thing. Now I typically add a second one. Okay, and so basically, in order for the laws of physics to be the same in all inertial reference frames, okay, according to Maxwell's equations, this means the speed of light is always independent of the observer. So some people include this, some don't. I kind of feel like it's so important that I put it in there. All right, and so this maybe it doesn't sound crazy, but this is really a crazy idea, and this was the key. Nobody had ever thought about trying this idea before Einstein. Okay, now what's going to happen is it's going to lead to a lot of interesting results. And so let's sort of see how this works. So let's look at two, give it a try. So here we have a race car driver, Sam, is heading down the final straightaway, approaching the finish line at 100 meters per second. His fans at the finish line are shouting. The speed of sound is 350 meters per second today. And so we're saying, how fast are the sound waves of the shouts approaching in Sam's reference frame? Okay, so think about this one, get an answer, and see what you think. All right, so I ended up getting 450. And so basically what you can do here, all right, so different ways to think about this one, but how I would do it, being technical, is taking our equations that we had, so something kind of like this. So it's ux prime equals ux minus velocity. And so here we've got, now this is tricky, so now there's Sam's frame, and he's in the S prime. And so he's moving with a velocity of 100 meters per second this way. And then the people who are screaming are in the S frame. And they're screaming, and it's going backwards at a speed of 350 meters per second. And so the speed in the unprimed frame is 350 meters per second negative, because it's going back in the negative direction, and it would be minus that 100. And so technically I would get negative 450 meters per second. And again, another way to think about this is like we were talking about before, because they're heading in the same direction, the relative speed will add. Okay, so because Sam's sort of running in to these shouts, they're going to speed up. Hopefully that makes sense to you. So now let's think about this identical situation, but now it's Susie with a race rocket, and the people, instead of yelling at her, are shooting laser beams at her at the speed of light. She's moving really fast, 1 times 10 to the 8th meters per second. How fast are the light waves approaching in Susie's reference frame? Okay, so this, you might have gotten tricked on this one. And so this goes back to the Einstein rule. So if we think about this as being sound, okay, the answer would have been D. But because it's light, it's different. Light no matter what. This is an important thing too, because we could ask you a question that talks about light, and no matter what's happening, the speed of light is always the same, 3 times 10 to the 8th. So this may not seem revolutionary to you, but basically in order for everybody to measure light with the same speed, we have to measure distance and time intervals differently. And so this idea of there being an effective time for everybody is not true. And so let's look at some examples that Knight talks about. So the first one is the idea of simultaneity. And it's the idea that if something happens simultaneously in one frame, what does that mean about another frame? And so there's this example that's a real popular one with a person that's on a little flatbed railroad car and one person that's not. And so we say there's 2 events here that are simultaneous, and so we have Ryan and Peggy. And so the 2 events are exploding fireworks or firecrackers. All right, and so we tell you at the beginning that these 2 events are simultaneous in Ryan's reference frame. And so these happen in exactly the same instant. So let's talk about how this works. So in Ryan's reference frame, so R and P are Ryan and Peggy. So the 2 firecrackers explode, and then what happens is Peggy on her railroad car moves to the right. So again, she must be going really fast for this to be noticeable. But you see here that she's moving closer to the right firework. And so according to Ryan, all right, the right firework hits her before the left one does. So here, sometime between this picture and the third picture, the right firework, she's seen the light from it, but the one coming from the left side hasn't reached her yet. And so these two now are reaching Ryan at the same time, and so he says, hey, those are simultaneous, because I saw the flashes came to me exactly the same time, and I know I was halfway in between them. All right, and so in Ryan's frame, Peggy saw the light flash from the right one first. Now, the only way that this can happen is a scenario like this. So in Peggy's frame, she's standing still, and Ryan is moving to the left with a speed of negative v. All right, and so the first firecracker explodes and sends a spark of light. Now this has to happen before the one on the left does, because it reaches her first, and speed of light is always the same in every frame, and so the light is going to move, and since she is equidistant from the two firecrackers, this one had to have gone off first. And so you see in the second picture, that one's light reaches her, and then the one on the left finally goes off, and then at some later date, or here it is, the two of them are actually reaching Ryan at the same time, who's moving to the left, and then later on the left one will finally reach Peggy. And so the two pictures add up in that they both agree who saw which firework first. But what's crazy is that what this means is that two events that happen at the same time in one frame won't happen at the same time in some other frame. And we call this the relativity of simultaneity. Here's another crazy idea. This is one of probably the more famous ideas out of this. And so to do this, we're going to talk about a little example. And suppose there was an astronaut in a little spaceship. The spaceship's got a height of h. So the astronaut shoots a laser beam from the top of his spaceship down to the floor off a mirror, and it bounces up to the top. And he records the time that it takes, or the astronaut records the time it takes to do this. And so, for instance, if the speed of light is c, all right, then we look at this and say, okay, the time it took for the astronaut to have this time go back and forth would be 2h divided by c. Now, if we look at this from a frame from somebody who's standing by watching, okay, then the astronaut, when she shoots her light beam down, it's going to be different. Okay, so the person watching it from the side is going to see the light beam coming down at some angle. Okay, and so you basically, because you're moving with some velocity, it's going to come through with some angle and then bounce up like this. So a person watching the astronaut shoot this from the ground, okay, so we call this length here basically L, and remember that the height over here is h, then the actual distance that this person sees the astronaut's light beam go is L squared plus h. And so now the elapsed time to someone watching it is 2, and it's a bigger number divided by c. So for the person watching this happen, the time is larger than for the astronaut. And so this effect is called time dilation. If you go through, like Knight does in the book, the equation you get for this looks kind of like this right here. Okay, and so it's an equation that it's a little bit complicated. It's got a square root in there. But this is the equation, and this is sometimes summarized with this idea that says moving clocks run slowly. We'll talk more about what this really means, but that's sort of what you see. And this is a real effect. Okay, if you do this, if you were to go really, really fast, close to the speed of light all the time, you would age slower than people who weren't doing that. To define this more clearly, we define what's called the proper time. So one question is people will have, what's the real time? Well, there is no real time. Okay, everybody measures the time differently, and we don't really have one that's the real one, but we have one that's called the proper time, and that's the time that's measured in the frame where the events happen at the same place. All right, so if you look at that example we were just talking about with the astronaut is the one that shoots the beam and then has it come right back to her at the same spot. So she's the one that measures the proper time. The person watching from the side sees the two events, which is where one event is the laser beam leaving, the other one is the laser beam coming back. She sees, or the person on the side sees those two things happening at a different point. And so, all observers measure what we call a correct time, but the proper time is just this definition. And so here's the equation, the way Knight will write it in terms of the proper time. And in fact, Knight makes another little tiny correction and writes it kind of like this here, which is just Some people do this, some people don't. Just a way to kind of clean it up. We call this beta equal to V over C. And then just a couple of examples. So one example that's always brought up is things called muons. So muons are particles that are created at the top of the atmosphere. Basically, they're created up there, and sometimes they come headed towards the Earth. Now these particles, when they're created, they have a lifetime of 1.5 microseconds. Now this isn't enough for them to survive to hit the Earth. All right, but because they're moving super fast generally, okay, then this whole idea of moving clocks run slowly, so they're the moving clock, and so there's more time, and so the muons actually, will hit the Earth. All right, and this is totally could not happen without relativity. Another thing is that GPS satellites, this is one example of things that we use a lot that's actually affected by relativity. They have to account for these time dilation effects. If it doesn't, the GPS software goes haywire and starts saying, you're 500 miles away from where you are within a couple of days or something. Okay, we'll talk more about this in class.